Thank you for watching our presentation video. I'm MISUMI. Our presentation title is Microscale Electrostatic Attach-detach Device for Self-reconfigurable Modular Robotic System. Self-reconfigurable robotic system, I call SMR, is composed of lots of unit robots. A unit robot has simple functionalities, for example, communication, sensing, and connection, and its shape is also simple. However, by connecting unit robots to each other, SMR has complex functionality as a group of robots. Just by changing the configuration, it forms various shapes. This is an example of SMR, Atron. It can perform like snake, clusterwalk, and car. One of the main topics about SMR is shrinking its unit robot. Minimization of unit robots increase their number in an SMR because more unit robots are contained in a certain space when they are smaller. And complex SMRs realize high functionalities and various shapes. These cubic robots are unit robots of M blocks. Its unit robot size is 50 millimeters and its actuator size is under 10 millimeters. While previous shown Atron's unit robot size is 110 millimeters and its actuator is 4 centimeters. Further miniaturization of unit robots realizes programmable matter. Its unit robots are called Catom. Catom is millimeter scale or smaller. Therefore, programmable matter contains thousands of unit robots, while previous shown SMRs are clusters of tens. Because of the characteristic, programmable matter is supposed to be a metamorphic robotic system and to be used as a programmable 3D printer. In order to work as a unit robot, Catom has processing units, communication units, batteries, sensors, and actuators. All of them should be millimeter scale or smaller. Let me focus on each component of Catom. About processing and communication, this group realized millimeter scale communicative MPU. About sensor, high efficiency photodiode can be utilized as a sensor. And about power source, high voltage photovoltaic cell array for driving actuator was proposed by Mori et al. However, attach-detach actuator for inter-Catom connection does not exist, and new device development is needed. It is millimeter scale, its strength is milligram order, its power consumption is low, and it can be integrated to a unit robot easily. Therefore, in our presentation, we propose attach-detach actuator for inter-Catom connection. Attach-detach actuator can utilize some mechanisms by mechanical structure, permanent magnet, vacuum, hot melt adhesive, electrostatic. Among these mechanisms, we chose electrostatic force as attaching mechanism because an electrostatic actuator is suitable to shrink. It has simple structure, just electrodes, and its strength is proportional to square of its dimension, while weight of microrobot is proportional to cubic. Karagosler and his colleagues researched on the microscale electrostatic actuator for Catom by microelectromechanical systems technology. Their Catom was able to form 2D configuration because its shape was cylindrical, which had actuators on the side. Therefore, an actuator must be placed in each direction for 3D shape formability. And it must be planar, because the requirements of the adhesive strength is severe in the 3D configuration. From this consideration, we propose a flexible electrostatic connecting device and its wrapping integration method. Our proposed device consists of electrostatic actuators and wires which provide them with driving energy on flexible substrate. The device is integrated to unit robot by wrapping it to 3D printed polyhedral rigid shell. This method realizes large contact area and simultaneous integration of wires with actuators. This is the design of our proposed device. It has T-shape, and its electrodes are sandwiched by flexible Pyridine C films. 5 actuators on horizontal bar and 3 conductive areas are on vertical bar. The lower end of vertical bar is connected to a driving circuit. Actuator is interdigitated electrodes. Its dimension is 805 micrometers by 850 micrometers. When the actuator faces to conductive surface, a voltage supply generates adhesive force. Assembly process of Catom with our device is shown. First, the device is wrapped to a robot shell. Then, other components are encapsulated in the shell, and the device is connected to a power source. Finally, the shell is closed. I explain the operation of our device on Catom. About attach action, by applying voltage to the device when they touch, Catoms connect to each other due to electrostatic attraction. About the detach action, on cancelling the electrostatic force by discharging electrons, Catoms detach by gravity force. In order to suspend Catom, adhesive force needs to overcome the gravity force of Catom. Therefore, we measured adhesive strength of our actuator to provide the information for SMR's shape design. For the measurement, we prepared 2 types of chips because a single actuator has so small adhesive force to measure its strength directly. One is active chip. It has 36 actuator electrodes, and the other is passive chip, which have 36 conductive areas. The area of each driving and passive electrodes were 815 micrometers in width and 805 micrometers in height. They are separated by a distance of 730 micrometers. These are the cross-sectional views of the actual device and the active chip of the test structure. There are 2 differences between them. Firstly, in the actual device, the electrodes are sandwiched by Pyridine C, while in the test structure, Pyridine C only covered the top side of the electrode. This configuration was necessary to prevent electrodes from being peeled off. The structural difference of the bottom side can be ignored when the active chip faces to the passive chip closely, because electric field only exists between the active chip and the passive chip. Secondly, electrode material on the test chip was aluminum silicon, not gold, but the kind of metal doesn't affect the strength of adhesion. This is the measurement setup. An active chip was fixed on a stand, which was installed force gauge. We put a passive chip on the active chip and applied voltage to the active chip. Next, we moved the force gauge up. Then, the passive chip was pulled up by the force gauge through springs. By Hooke's law, the pulling force of force gauge is proportional to its displacement. When the pulling force overcame the adhesive strength and the weight of the springs and the passive chip, the active chip and the passive chip detached and the force gauge indicates the maximum pulling force. After that, the pulling force balanced with the gravity force. Therefore, we calculated the adhesive strength by subtracting the gravity force from the maximum pulling force. This is the result of the adhesive strength measurement. The data is fitted by the second-order polynomial, 1.43 times 10 to the minus third V squared. From the fitting curve, we estimated test structure's adhesive force was 3.58 millinewtons at 50 volts. Therefore, a single actuator operated at 50 volts can suspend 10.1 milligram weight. This value is sufficiently large to suspend the micro-robot shell. Because we confirmed that the actuator was useful, we fabricated the flexible electrostatic connection device. This is fabrication process of our flexible device. First, 2 micrometer thick polyethylene C was deposited on silicon substrate for handling. Next, 30 nanometer titanium and 100 nanometer thick gold were spattered and patterned by wet etching. After the patterning, 2 micrometer thick polyethylene C was deposited on top. By sandwiching electrodes with polyethylene C, self-peel-off of electrodes was prevented while wrapping our device to a unit robot shell. Then, 100 nanometer thick aluminum silicon alloy was spattered and etched to form the outline of the device. Because polyethylene C has chemical inertness, it was etched by O2 plasma etching with aluminum silicon mask. After patterning of polyethylene, the device was peeled from silicon substrate by surface tension of aluminum etchant while an aluminum silicon mask removal. When the device did not come off, an ultrasonic cleaner was utilized. This picture shows the device wrapped to the shell. Wrinkles were due to manual operation. Wrapping my micromanipulator will eliminate them. We did the suspension demonstration. Due to the lack of a microscale driving circuit, we suspended the unit robot shell with our proposed device by the active chip. This is the shell. It was suspended. However, the shell didn't detach spontaneously after turning off the voltage. But it should be noted that unit robot in the final form is heavier, because it includes processing unit, battery, and voltage up converter. And therefore, it will certainly attach and detach according to applied voltage. In conclusion, we proposed a microscale electrostatic attach-detach device for connection of SMR. Our proposed device is flexible and it is integrated to your unit robot by wrapping. We measured the strength of our device and we estimated that the single actuator could suspend a 10.1 mg weight. We demonstrated attach action of unit robot shell with our device. Thank you for your listening.